I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on springs, Hooke's Law, and potential energy. In this series of videos, we're going to talk about energy, work, and power. And we're going to start with energy in springs and learn about Hooke's Law and potential energy in springs. What we are going to do is we're going to conduct a lab experiment and look at a graph of force versus the stretch of a spring. So we're going to graph force on the y-axis because it's dependent upon how far the spring is stretched. And when we collected our data and we graphed it, what we found is that the graph was a straight line. So a direct relationship between force and displacement or stretch of a spring. So we're going to write our slope-intercept form of a line, y equals mx plus b. And what we know is that the moment we applied a force, the spring started to stretch, which means that the y-intercept is going to be 0. So we can cross that out. So now we're going to replace y, m, and x with F is equal to 50 newtons per meter times x. The 50 newtons per meter is something called the spring constant. The spring constant is specific to each spring, and it's defined as the amount of force required to stretch the spring 1 full meter. So in the case of our lab, we only collected data up to 0.5 meter. Now, the generic equation is F equals Kx, and this is Hooke's law. That applies for every spring. So any spring constant, we can figure out how much force is required to stretch that spring. When we look at springs in graphs, if you stretch a spring a certain distance x by applying a force, and we create a graph of force versus stretch of that spring, it's going to be a straight line. So as we saw before. Now, if we compress the same spring, Hooke's law takes into account absolute values. So this is going to be the same graph. And we're going to talk about ideal springs. And what is an ideal spring? An ideal spring is one where mass is negligible. So the mass does not factor in for the spring. An ideal spring also obeys Hooke's law. Notice the equation absolute value of Fs is equal to K times the absolute value of X. So Fs is the restoring force. What is a restoring force? Well, the restoring force, a spring wants to be at its resting length. So if you stretch it or compress it, it's going to have a force that wants to get back to that resting location, also known as equilibrium. So the restoring force is pulling or pushing back towards that equilibrium. K is the spring constant in newtons per meter, as we learned in the previous slide, and X is the displacement measured in meters. Now we're going to talk about energy, and the way we find energy is the area underneath a force versus stretch graph. So let's look a little bit more with energy. So we have potential energy. Potential energy is the energy that an object possesses by virtue of its position, meaning where it is, or configuration. So a spring would be stretched or compressed. That would be a configuration. It's represented by the capital letter U. Not quite sure why U is used. The best I could find is that it was written in a paper. Potential energy was U somewhere around the turn of the century, 1900s. So that's why we use U. So some examples: gravitational potential energy and stored spring energy. So let's look a little more into stored spring potential energy. So we have our force versus stretch graph, and what we talked about is the area underneath that graph is the stored potential energy. So the area of a triangle is 1/2 base times height. And we know that that area is the stored spring energy, and we're going to use US to show that it's spring energy. And that equals 1/2 the height times the base, which is 1/2 Fx. Now, the reason F is in a different color is because most times we're not going to know the force. We're going to know the spring constant and how far it's stretched. So we can use Hooke's law and substitute in 1/2 Kx for force times x, and that simplifies to 1/2 Kx squared, which is the equation to find potential energy. So springs possess potential energy when stretched or compressed. The formula, as we derived from the last slide, is US equals 1/2 Kx squared, where stored energy is measured in joules, K is the spring constant in newtons per meter, and X is how much the spring is stretched or compressed, measured in meters. So let's look at the units. So units are a joule, which is a newton times meter. A couple of these other ones, the British system is a foot-pound, not used, and erg is not used in Physics 1, but they're just information. Now, the atomic level electron volt is something that you would use when you take Physics 2. So, a little bit more about the Joule. It's named after James Prescott Joule, who perfected the steam engine. So, the SI unit for force is Newton, SI for length is meters, and a unit for a joule is a Newton times meter. So, by definition, a joule, 1 joule of work, is done when 1 Newton of force causes an object to move 1 meter. So, where's a spring's potential energy zero? Well, when it's at its preferred or equilibrium position. You'll see this word equilibrium for springs a lot. This means that the spring's not stretched nor compressed. So this is Hooke's law and stored potential energy in springs. I hope this was helpful. I hope you have a great day and an even better tomorrow.
If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter at Cavi Coaches.